Ladies and gentlemen, welcome to the Royal Society. I'm Mike Gordon, a member of the committee that selected Gordon Plotkin, Professor of Computer Science at the University of Edinburgh, as the very first recipient of the Royal Society Milner Award. So before I say a little bit about the Milner Award and about Gordon, I've been asked to first apologize that this event is not being webcast live for reasons, quote, beyond our control. But it is being recorded, so you're asked to mute your mobile phone and to avoid noises and other interruptions which would damage the recording. The Royal Society Milner Award, supported by Microsoft Research, is a new award given annually for outstanding achievement in computer science by a European researcher. It's named in honor of the late Robin Milner, FRS, a pioneer in computer science. The recipient is chosen by the Council of the Royal Society on the recommendation of the Milner Award Committee, which is made up of Fellows of the Royal Society, members of the French Academy of Sciences, and members of the German Academy of Sciences Leopoldina. Professor Plotkin's research contributions include work on hypothesis discovery, theorem proving, situation theory, non-standard logics and category theory, but he may be best known for his work on the semantics and logic of programming languages, with contributions to operational semantics, logical frameworks, concurrency, domain theory, security, type theory, lambda calculus, full abstraction, abstract syntax, non-determinism, and probabilistic computation. His current interests include the theory of algebraic computational effects and computational systems biology. Before the presentation of his award, Professor Plotkin will deliver a lecture entitled From Logic to Computer Science, a Linguistic Journey. It's my great pleasure to introduce the first winner of the Royal Society Milner Award, Professor Gordon Plotkin.
Just a moment. Well, it's such an enormous honor to be recipient of the Milner Award, and never mind the first one. That's too much honor to contemplate, perhaps. And it's fantastic to see everyone here this evening. When I came in earlier, it was absolutely empty. I couldn't believe so many people would come, and that's really another honor for all of you, for all of you to come here to listen to me. I can't imagine why the converse could be true. The Milner Award is obviously aptly named because of the great achievement of Robin Milner. But it means a lot to me personally because he was my colleague for many years. We didn't perhaps work together, or we did work together, but honestly it felt a bit more like we were sort of thinking together. And so he's quite close to me. So what I want to do, of course, obviously I'll talk about my own work. I certainly won't talk about all of my own work, just one thread. And in fact, my talk is simply one or two threads put together from a vast tapestry that's the contribution of computer science overall. But computer science per se is a part of a journey, and it has its roots in its own subject, its own development, of course, a lot of technological roots. It has roots in mathematics and statistics, but in particular, it has roots in logic. So I want to talk about its roots in logic, and I can't even talk about that. I can only talk about a very small part of it. But hopefully, you'll enjoy it as much as I will, perhaps more. But let me set the context, which actually isn't logic. I just thought it'd be nice just to make a very general look at computer science and physics. They seem to be quite strongly contrasting. So just think about physics. The state, you're looking at states, and the states are continuous. You've got your planets, which are somewhere in space. The motion, the stately motion of the planets, is a continuous motion. And the motion of physical systems are governed by physical laws, which are expressed mathematically by differential equations. In contrast, it's almost a contrast in every detail. In computer science, the state is symbolic or discrete. I mean, we all know that memory is discrete. All these zeros and ones in computers, but everything's discrete. The state of your interaction with a page on the internet, that's completely discrete. Have you put in your password? Haven't you put in your password? What's your password? All these kinds of things. Dynamics is less obviously discrete. If you look at machines, they're largely discrete. They may have a central clock, and everything's synchronized with the ticks of that central clock. But more important part of discreteness is the discreteness that arises from computer programs, because they move from state to state. Now, computer programs are the analogs of the laws of physics, but they're man-made laws. You declare how your machine is going to work. And really, this talk came out to be about rules more than anything else, rules for this movement. So you can think of these rules, but the rules will have actually two functions in the talk. One is indirectly to do operational semantics, which Mike already mentioned, to specify how programs work. The other is quite directly to use the rules as a programming language themselves. That's not at all new, but the context, which will be biological, may be a bit new to some of you. OK, so roughly, rules and differential equations kind of correspond to each other. So you should remember that, because we'll come back to the thought, but a lot later. So let's begin with logic in the early 20s of the last century. And here are three quotes. Hilbert, the best logician of the 20th century, according to Hardy, the one at the bottom, best British mathematician, perhaps. Sorry, Hilbert, the best mathematician. Every definite mathematical problem must be capable of a solution. In mathematics, he declared, because he was very good, there is no ignorabimus. We will not be ignorant. At least Hilbert was only rarely ignorant. It got a bit more precise by 1928. He said, is mathematics decidable? Is there a definite method to decide of any mathematical assertion whether it is true? To which Hardy, perhaps you already read this, said, there is, of course, no such theorem. If there were, we should have a mechanical set of rules for the solution of all mathematical problems, and our activities as mathematicians would come to an end. That's clearly a logical proof. Anyhow, the question is there a mathematical question in all these words? And there's clues, you see. The clues are given in red. So we have to decide of any mathematical assertion. So we'd better find the mathematics of mathematical assertions. Mathematics of mathematics is called metamathematics. And this is the beginning of metamathematics in this period. Whether it is true or provable, Hilbert wanted to decide whether things were true. But Gödel showed him there were a few difficulties in the way. So one can just as well ask the same question about provability, once you know what provability means, that is. And the question is, what are a mechanical set of rules? So we need to answer three questions. What's a mathematical assertion? What does it mean for it to be provable? What's a mechanical set of rules? And then, is it the case that there is or there is not a mechanical set of rules for deciding every mathematical statement? Or we should be more modest. Maybe not every mathematical statement. Let's limit ourselves to some area of mathematics, like arithmetic. That's not a randomly chosen area. So for those of you, well, so let me see. When I was preparing this lecture, I was told it was for a general audience. But unfortunately, my work's got lots of symbols. So I'm going to take you through lots of symbols. I want to give some detail. I don't like these lectures where they just say a little about a lot. I'd rather do the converse. But I hope our symbolic journey will be a pleasurable one. I'll try to make it understandable. Anyway, Turing machines are really easy. You've got a state. You've got a reading head. The state's kind of repeated here for some reason. And you've got a tape. So it's got 1, 1, 0, 0, 0 on it. Happens to be, use it for both input and output. And all that this head does is it moves from left to right. It reads what's there, and it writes. That's it. So we're in the starting state QS. So what happens next? Well, in this head, there's a rule for what to do next. The starting state QS says, oh, look, I'm reading 1. So I'll move into state Q super 1. The super 1 just means, well, I remember that I read 1. And while I'm at it, I'll leave that 1 alone. I'll print that 1 as 1, and I'll move to the right. So that's just this, right? Big deal. So it keeps moving to the right, staying in Q1. All Q1 does, actually, is moving to the right, waiting for a blank. So it eventually gets there, and whoops, there's a blank. So what's it going to do? So I'm in Q1. I see a blank. I'll move to the final state, QF, and I'll put a 1 on that blank, and I'll stay where I am. N means neutral. OK? So it's me. I've done that. That's what there is to Turing machines, nothing more. But what do they do, you see? Well, one point of view is that they work in words. Words are just sequences of letters. In this case, we've got letters 1, 1, 0, 0, 0. And all we've done is moved all the way to the right and stuck a 1 in the end. Okay? But another point of view, of course, is that some words actually mean numbers. If you remember your binary system, this number is 1 times 16 plus 1, blah, 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 and that's actually 24 in decimal. And this number here is 2 times 24 plus 1. So this Turing machine is almost, but not quite true to say, computes the function 2 times plus 1. You can try to think why it's not quite true to say that, but if you know Turing machines. Anyway, it's almost true, so we'll just pretend it's true. Oh, okay. So the question is, going back to the earlier slide, what does it mean to be mechanically decidable? What does it mean to have a mechanism to do that? In fact, there were a bunch of answers, but perhaps the main ones were due to Herbrand and Gödel functions, Alonzo-Church, Lambda calculus. I mean, I'm not going to say what these are, and Alan Turing with Turing machines. And Gödel, who was somehow the prince of logicians, said, first two are no good, but the third one is just right. And that's why I told you the third one. It's obvious that this is a mechanical procedure. It's much less obvious that any mechanical procedure can be done that way, and you have to give an analysis, and that's what Turing did, but let's not go there. Gödel liked it. That's good enough. Okay. An important point, though, is although this is good as a philosophical analysis of computability, mathematically, the three things are completely equivalent. And it's not very hard to prove. They allow the same things to be computable. Of course, Turing machines are a little bit schizophrenic. Do we mean they're computing functions like 2 plus 1 from numbers to numbers? Or do they mean that we're computing functions in strings like put a 1 in the end? But whichever way you talk about it, they still do the same things. So that's good news. So this is just a very brief account of, so that's the first part done. That's mechanical means. Now we need to see what logic is. So I'm going to try to do logic in one slide. So we have arithmetic expressions like 1 plus 2 times 3 plus 4, or x squared plus y squared. We have arithmetic predicates like 1 plus 2 blah, blah, blah is equal to x, which it may or may not be depending on what x is. We've got arithmetic formulas. There's one. There are non-zero numbers x, y, and z such that x cubed plus y cubed equals z cubed, which you'll all recognize as being false, because that's a part of Fermat's last theorem. But in mathematics, we just don't like all these words, so we just write that instead. But it's exactly the same thing. That just says, that's just another way of saying there are. That says not equal to. So it looks nicer. It's also shorter. Maybe that's the main thing. Okay. And then you have to have a way of proving things. And to prove things, you have a bunch of axioms and a bunch of rules. So an axiom is 0 not equal to 1. And there's an axiom of logic. If f and g, if you can prove f and g, then from that follows f. F and g implies f. So it's a single, implies is a symbol of the logic. That's just the statement f and g implies f is true, or as an axiom. And you have rules. If you've proved f, you've proved f implies g, then you've proved g. So what you should do when you see that is you think that, have the following thought. Mathematics is a meaningless game. This is the formalist point of view. At least it's a way to understand this. All that mathematics is about strings of symbols, whatever these mathematicians are writing on the page. And all we do with these strings of symbols is we move from one to the other by rules, sort of playing with these strings. If this string looks like that, this string looks like that, then that string looks like this. And so since it's just a game with strings, or perhaps a less unpleasant way of putting it is since part of mathematics is just a game with strings, Turing machines can play these games. So Turing machines can perfectly well be programmed or thought of as working on mathematical statements and deciding or not whether they're theorems. So this is how you would do it. Suppose you're interested in this particular case of Fermat's last theorem. You don't know the answer, but you've got a Turing machine which is pretty good. So you're going to ask it, what's the answer? So you just regard that as a string of symbols. You want a few brackets to make it unambiguous, and you write it out on a tape, rather a longer tape than the 111000. So your tapes are going to get pretty long. And you let the Turing machine run. And since this is a clever Turing machine, it'll eventually get to final state QF. And when it's finished, it'll just tell you the answer. It'll either say YES, or it'll say NO. So we're allowed to use letters from any alphabet, including English. So a Turing machine that given any statement of arithmetic, and then it always terminates either giving you yes or no, and it should be correct. It's called the decision method for arithmetic. So Hilbert's question, the Entscheidung's problem is there a decision method for arithmetic? And I won't keep you too upset. The answer is no, which certainly upset Hilbert, but would have pleased Hardy. But the interesting thing is that that was proved by two people, Alonzo Church, 1936, using lambda expressions, and Alan Turing using Turing machines. And the way they did it, let me just look at Alan Turing's way. He said, there's no Turing machine which can decide for any given Turing machine a starting tape where the given Turing machine halts on that tape. So it's not directly thinking about arithmetic. It's just there's no Turing machine which understands all possible Turing machines. But it turns out that understanding a Turing machine can be expressed in terms of arithmetic. And so therefore, you can't decide arithmetic either. But I won't go into any details. That's the idea. So it just so happens that anyone who knows a bit of computer science knows absolutely everything I've just said. So I wanted to talk about someone that people may not have heard about so much. And the point about this bit of the talk isn't only to talk about Emil Post, but it's the work of Emil Post that's the precursor of the work I did on operational semantics, not that other work, although it's the main line. So Emil Post had a short life, in a way a sad life, because he wanted to be an astronomer, but when he was playing in the street as a young fellow, a car ran over his left arm and removed it. So that was sad. And later on, he got bipolar disease. And he was forbidden by his doctor for doing research for more than, I think, 2 hours or 3 hours a day. But he did a tremendous amount. It's fantastic what he did. Although this particular part isn't a cheerful bit of the story, he did a lot more work than I'm going to talk about here. This is just part of the story. So he was really brilliant. And so he did work in 1920-21, which anticipated all the work I've just been talking about. He wrote it up in 1941. Actually, he wrote it up a bit earlier, but it was rejected by the American Journal of Mathematics. He wrote it up again in 1941. It was rejected because it was too late, because the other guys had published in 1936. And then finally, sadly, it was published posthumously in 1965. So there's a story. Anyhow, let's see what Emil did. So I just want to start off with another little game of his. And I guess I should go through this fairly quickly. It's a game called Tag. And I've chosen this game called Tag because it can make Emil's production systems, which we're going to talk about, more evident. So how does Tag work? Well, it's a game with strings. You see, it's even more formal. It's a guaranteed meaningless game. You're allowed to change 0 to 0, 0. If you've got a 1, then 0, 0. If you've got a 1, then 1, 1, 0, 1. And then there's a number 3. So how does this all work? There's 1, 0. So it begins with a 1. So you take 1, 1, 0, 1, and you stick it on the end. The next thing you do is you notice the first 3 symbols are 1, 0, 1, so you remove them. Then you play the game again. You just keep playing the game. On you go. And the question is, you see the strings seem to be getting bigger and bigger. Well, as a matter of fact, the next string is going to get smaller, if you think about it, because the 0, 1, 1 is going to get removed. That's removing 3, and you're going to put 2 in then, so you're going to decrease by 1. So the question is really, given a system of rules, given an initial string, are you ever going to get to the empty symbol? How hard can that be to decide? The answer is as hard as anything else. That's what Minsky showed in 1961. There's no Turing machine which can decide whether any given tag system initial string ever produces the empty string. In fact, these tag systems are as complete as any other model of computation. It's just harder to show that. So I want to use the tag systems to illustrate post-production systems. So here are our tag system. Now, if you think about how does this work, it's kind of a clunky thing. We'd just like to make it smoother. So let's think of a string that begins with 3 zeros and then something. Well, what's the tag system going to do with that? Well, it'll see the 0, and it'll stick 2 zeros on the end, and it'll remove the first 3 zeros. So it'll send 0, 0, 0, some string to some string 0, 0. So equivalently, writing variables instead of English, 0, 0, 0, x goes to x, 0, 0. OK? And you can write, these are all the rules for strings beginning with a 0 and of length at least 3. And there's other rules for strings beginning with 1. There's for strings shorter than 3 in length. But what's the deal? The deal is that the tag system, the initial string 1, 0, can be returned into the empty string using the tag rules. Is the same as saying the empty string can be derived from the initial string 1, 0 using the production rules. That may seem rather a large amount of breath to use for very little. But the point is that these production rules are easy to use, much easier than tag system to code anything. So let me just say, I haven't said what tag systems are in general, so let me say that quickly. Suppose we have some letters from an alphabet like 0, 0, 1, and some letters might be 0, 0, 1, 1, 1, whatever you like. Then you put the letter x, that's for a variable, some more letters y, yet more letters y, another bunch of letters x, x. blah, blah, blah. So let's write W for the various kinds of letters and X's for the variables. And this rule becomes W1X, W2, that goes to that. And this kind of rule, see, these are called terms. They're called word terms. They're mixtures of specific letters and variables. So they look like that in general. And the general form of a tag rule, a production rule is that T1 through Tn goes to U. So the idea of this thing is you think of this as a very formal kind of mathematics. If I've proved T1 through Tn, then I've proved U. That's the idea there. There's an example binary rule. If I've proved X, and I've proved X implies Y, then I've proved Y, which, of course, is the rule you saw before, but now it's within a production system. So you can see it's very easy to believe that production systems can encode logic, and they certainly can. It's also the case that they can encode Turing machines, and it's very easy to do that, too. For example, if you take this thing here, you're in the start state, you just write the tape on the string, and you put the head just before the letter that you're currently scanning. So if you see QS1, that should go to 1Q1 using these rules, and you move to the right, so that's why the Q1's after the 1. I won't go into any detail. It's just very easy to do. So all these systems are quite equivalent. So let's see what Emil Post actually did. Well, I'd like to say that he proved there's no canonical system which can decide if any given canonical system can derive a given word, because that would be the analog of every Turing machine. There's no Turing machine which understands all Turing machines. There's no tag system which understands, there's no production system which understands all production systems. But he didn't. It's really annoying. If you read his paper, he almost did. He had the idea of the diagonal idea. He had the idea of mechanical decisions. But he didn't quite put something together. I felt, if it only did a decent referee, the referee would have said, well, just rearrange things a bit. So I think morally, he did prove the first part. I think one would give him 8 points out of 10 or something. He didn't get quite as far as Entscheidung's problem. He was working on his own, and he wasn't in a good work situation, unlike these other guys who were professors at Princeton or Vienna or something. Anyway, he did really well, and his work should have been better known. So let me just put that to one side and do something else, and I'll make the link later with the operational semantics of programming languages. Let's suppose we have the amazing task of wanting to evaluate 1 plus 2 times 3 plus 4. You may already have done it. But what was the first thing you did? Probably the first thing you did was notice that 1 plus 2 was 3. This is exciting. OK, so you went to 3 plus 3 plus 4. The second thing you might have done is notice that 3 plus 4 was 7. And then in the final act of genius, internal genius, you notice the whole thing was 21. Oops, there it goes. OK, so let's just look at that single first act of genius. You notice that 1 plus 2, if I'm going to evaluate 1 plus 2 times 3 plus 4, I better use the fact that 1 plus 2 goes to 3, and I'll change this 1 plus 2 to a 3. OK? Let's look at a slightly more complicated situation. Suppose I want to evaluate 1 plus 2 minus 1 times 3 plus 4, what that goes to. Well, I have to evaluate 1 plus 2 minus 1. So now I've got this sub-problem here. I'll actually look at the 1 plus 2, of course, but I'll go from there to 3 minus 1, and I'll substitute in here. So what I'm trying to get at is what's the general pattern of what's going on. So here's the general pattern. If the first expression goes to some version, a transformed version, then the first expression times 3 plus 4 goes to the first expression transformed times 3 plus 4. As always, let's see, what's the next slide? Ah, yes. So, so the 3 plus 4 could be anything. That's the second expression. As I said before, using English, you run out of symbols too quickly. You run out of space, so you just use symbols instead. So E1 is the first expression. E1 is the first expression transformed. And, of course, we'll put an E2 for the second expression. And there's nothing special about times. There might be any operation, arithmetic operation, plus, times, divides. So that's a general rule there for how to evaluate an arithmetic expression which looks like E1 op E2. What happens in your act of genius? Once you'd finished evaluating the first thing, you went on to the second one. What you're doing was implicitly following this rule. If I want to evaluate K op E2, first of all, you evaluate E2, and then evaluate K op E2 prime. Once you've done all this, in the very end, you're going to have something like 1 plus 2 goes to 3. So, in fact, the rules divide into two classes. These ones which are just kind of messing around inside expressions, and these ones which are actually doing a bit of work. And these ones are called redexes in the trade. OK. A point here, which I hope kind of seeped in without noticing, is that we're no longer working with strings. We think of arithmetic expressions a bit differently. Arithmetic expressions, we are analyzing them. We have to evaluate E1 plus E2. So we're not looking at some string, blah, 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 blah. There's a plus somewhere in the middle, blah, 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 blah. We just conceive an arithmetic expression, whether it's a number, a variable, or some operation applied to some arguments. So they have structure. So this is called abstract syntax. We just look at syntax in this way. And for those of you who know a bit of linguistics, in linguistics, this thing is completely major. That's pretty important in computer science, too. You put in a sequence of English words, that makes a sentence, but you have to parse the sentence. You have to find out what the deep structure of it is. And so in computer languages, you also have this surface structure, which programs are nothing but sequences of symbols. And you need that, because that's what you're feeding to the computer. But to analyze it, you need to understand them as structured in some way. So that's what's going on here. And that's a thing that's used a lot. So let's just do another example, probably too quickly. I wonder, so you can have commands. Actually, I'll just point to what, I think I'm not going to do this. So a command is either an assignment or a sequence, one command after another, or a conditional, or a while, or a skip. And for example, this one here says, if B is true, do C1, otherwise do C2. This one here, X becomes E, says, figure out what E is and make that the value of X. And we use some Boolean expressions. So here's an execution sequence. So suppose we want to actually execute a command. Well, what do? Well, we start off with X becomes 3, but we can't make X equal to 3 because we ain't got any place to do it. So we add a place in. So we say, suppose at the moment X is 1 and Y is 4, then after that, X is 3 and Y is 4. And so then you have to look at skip. And so that's, when you finish X becomes 3 equals 3. When you finish a command, it becomes skip. So then we've finished that. So we've gone through this. Now we need to see whether or not X equals Y. Well, after a while, we find that X isn't equal Y. I mean, you can see that yourself, because there it's 3 and there it's 4. So if false, then something. So since it's false, we look at the first branch, which is X becomes 4. And finally, oh, what's happened there? Oh, no, it's false, so it's Y becomes equal to 5. So Y becomes equal to 5, and that sets Y to 5, and we're done. So hopefully, I went through it far too fast, but hopefully you'll get the same feeling of mechanical procedure. And there's also rules for it, and they're basically no different to the previous rules. It's easier to understand the first bunch of the rules if you don't look at the state. So for example, if you look at the second one, it says if true, then do C1, else do C2. So that simply means you have to do C1 next. What else could it possibly mean? The state never changes between one move and another. And finally, assignment actually does change the state. It makes the new value of X in the state. So that's the general thing. So that's a very fast introduction to operational semantics. The question is, what on earth has that got to do with Emil Post? Well, it must have something to do with him, because we've both got rules. I've got these kinds of rules, and he had production rules. Is there any commonality between these kinds of rules and production rules? Well, let's look at it. We could make it more mathematical by writing, arrow is a predicate. This says E1 moves to E1 prime in one step of evaluation. So let's just write arrow of the two arguments. Oh, I didn't correct that. Arrow is a particular predicate. You could imagine just putting in any predicates. And you could imagine that the E's aren't arithmetic expressions, but any kind of expressions from any area of mathematics or ordinary life. Now let's look at a post-production rule. What does that look like? Well, it's got some arguments, some weight T1 through Tn and an arrow, but we can just as well write it a bit more two-dimensionally than that without losing anything very much. These T's and U's were actually strings, remember, rather than expressions. But in fact, what I've showed you there is post-production rule in canonical form C. There are also canonical forms A, B, and D. So canonical form B was actually expressions, and we could just as well write provable there. And now these and these are much the same. The only difference is that these predicate symbols have several arguments, and here we have several premises. But you could easily imagine a common form which had allowed both of these possibilities, and these are called Horn rules. So there's a definite commonality, and that is the intellectual root. So as a matter of fact, I didn't know about Post in such detail until this lecture, and the root went in a different way. The root went from Post to Smolyan, elementary form systems, and then to me. But there were many antecedents of structural operational semantics. It's a big subject. I've hardly had time to do more than give you an introduction to the very first part of it. But what I want to point out, though, is that all the people in green, or all the people whose names are written in green, are logicians. And so that shows, and you can see later on the non-logicians were beginning to enter into things. There's a mixture of logicians and computer scientists. And in fact, nowadays there are people who might not care to be classified as either computer scientists or logicians, rather they're both. They're theoretical computer scientists or applied logicians. So everything's coming together, and it's come together from a very long time ago. So you might ask, however much fun you thought that was, what's the point? What use is it? So I'd like to skip forward to a use which will be close to your heart, or at least close to your wallet, which is an application of these ideas in 2011 due to these people. And here's the general situation. Suppose you've got a web page, and you're happily writing all your details, your passwords on it, and the web page has got an advert. Now, the way that adverts work is there's an advertising company that sends I should say before, the way these adverts work is that they actually run programs on your machine. They send you programs to run on your machine. How do you know these aren't bad programs? So here, this advertising company called Ad Publisher is publishing an ad called Ad 1. And in here, this appears in the HTML. That's the thing that makes this thing work. And what this thing says, load this program, ad1.js, and run it on your nice little computer. And it can be any program at all. It might be a program written by a bad guy. This bad guy has direct access to it's called the JavaScript DOM, all the information on that page, which, by the way, has your password. So you can perfectly well steal your password and send it off. So look, obviously, this is a well-known fact, and we don't want this to happen. So what do we do with this code, the program? We can't just allow it to run willy-nilly. What you do is you regard it as an unruly child, and you put it in a sandbox. It's only allowed to play in the sandbox. Well, here's the architecture. You put it in a sandbox. And it's not allowed to talk directly to the DOM, to the information that's there. It's only allowed to do it through something called an API, an application programming interface. These are kind of bunch of, I don't know how you call it. Anyway, these are programs which it's allowed to call. And these are supposed to be programs that keep safety for you. So basically, that's the program that might be an evil person's program. Everything else is trusted. You look at what this system, the sandboxing systems do is, if they see any particular obvious horrors or less obvious horrors, they filter them out. They just fling the program away. If they see some things that look like insecurities, they rewrite them. So they do the best they can, and you try to rewrite them so that they're in some standard language for which you believe there's safety. So this is what Facebook does. Their language is FPGS. This is what Yahoo does, AD Safe. This is what Google does, is Kaya. You guys use this stuff every day, all the time. So what these people did was they invented a different language, which is called SES Lite, which actually is simpler than those other ones, but it's more amenable to mathematical analysis, and is part of the more or less almost the most recent release of JavaScript. I won't go into any detail. I'd like to show you the abstract syntax of it, not because I imagine you can read it, but let's just show you it's not such a big deal compared to the abstract syntax. Before we had like a couple of pages of abstract syntax, one for expressions and one for commands. It turns out there's only like 3 pages. That's the abstract syntax of this language. It's quite small, and it has an operational semantics. It's actually quite small. It's about 7 pages. So it's not too much worse than before. You'll see some old friends there in red. Anyhow, so it's a kind of continuation of where we were in the 80s, but adapted. So the question is, what can we do? We have to show that our system, our APIs, no matter what bad program we put in there, what possibly bad program we put in there is safe. How can we do that? Well, the answer is you can't. Because a program in this language, like any other language, is as powerful as arbitrary Turing machines. So you can't decide any property of it. So you have to do what's called a program analysis. You have to provide an approximation to the program, which you can analyze and gives you some information about the program. The art of the matter is to make effective approximations. So this is the general plan. Given the state and the APIs and the unknown trusted program, you turn them into a set of data log rules. Data log rules are another kind of rule. They're much easier to understand and to analyze than the previous kinds of rule. and they approximate the way the program works. And you prove a theorem that if E accesses a critical reference, let's just say if E does something bad, without going into technicalities, then that can be proved using the data log rules and axioms. This is a theorem that's proved using the operational semantics of the language. If we turn that the other way around, if you can't prove using the data log rules and axioms that a critical reference, that a bad thing happens, then E is safe. But this thing that you can't prove something is actually relatively easy to check in data log. So it's a perfectly decidable thing. So that's jolly good. What happens if you can prove using the data log rules and axioms that a critical reference is accessed? Well, E still may be safe, but it might not. You don't know. You'll have a clue because you can look at the proof, and maybe that will tell you about something about E. So you have to look at it by hand. So I think I won't go into this in much detail, except that I just want to point out there's a rule in data log. And so you see we've got predicates again, but here we've only got variables. We don't have expressions like before. And the fact that you only have variables is what makes this kind of thing decidable and efficiently decidable. And that was one of the great things about data log. So the team used these ideas, and they applied it to Yahoo's AdSafe. And Yahoo's AdSafe API, which had been running for some years, failed the test. These two things were the culprits. So we know it's failed. So you can look at the proofs. And by looking at the proofs, they converted the proofs to exploits. An exploit is a program E such that a bad guy can use E to gain access to your password. And showed it's perfectly possible to do so. But in fact, pleasantly, it turned out a small change to one of those programs was found when the APIs did pass the test. And as you may imagine, Yahoo adopted the change, presumably at some speed, anyhow. So that particular problem is gone. But it is interesting that programmers in these places like Yahoo are immensely clever. They understand every detail of how they work. And these particular API programs are quite small. But nonetheless, they're subtle. And it's really good that there are tools like this which can help keep things secure. And for me, it's a pleasure that they're to do with operational semantics. Let me turn in my last few minutes to, so here we've used rules to understand programming languages. Now I want to use rules as programs. And in fact, if we look at chemistry, then actually they always did use rules. In school, you always called reactions. You know, if you've got two hydrogens in oxygen, it goes to 2H2O, so that's burning hydrogen. Looks like this in the space shuttle. If you've got methane in two oxygens, it goes to carbon dioxide and two hydrogens, and it looks like this in a natural gas flare. Natural gas is something like 60% methane. So as an example, I wanted to run those two reactions together. I mean, actually doing that would be a major explosion. This is very theoretical, and it's only part of the actual chemistry is extraordinarily complicated. This is just an academic exercise in truth, but it has this pleasant, explosive background. So suppose we've got two methanes, 6 hydrogens, and 4 oxygens. Then there's enough there to run a bit of methane off to carbon dioxide, and then there's enough to run a bit of water off to, hydrogen oxygen to get some water, and you carry on doing that. But that shows you how these things work. It doesn't actually show you anything of reality. What happens in reality? How fast do these reactions go? And that's what's important, to look at reaction speed. And so, in fact, reactions have speeds. This one is K1. In fact, hydrogen burns something like, I can't remember the numbers, 5.6 or 6.5 times as fast as methane. So you have to look at these speeds. And I think I'll skip the details. But basically, suppose suppose the hydrogen went twice as fast as the methane, then it's basically got twice the chance. If you look at any particular reaction, it's got twice the chance of occurring first. So the way we're going to simulate reactions is we do one reaction at a time. We pick a reaction probabilistically according to which is the faster rate, using this formula, and we prove a time that's going to happen according to an exponential distribution, which I'm not going to talk about, and then we can do simulations of reactions. So this is what I want to do. I want to simulate chemical systems. Actually, I don't want to do that. I want to simulate biological systems, but this is the place to start. And then you get some graph that looks like this. Let's see if we can take a point of, for example, the green is the methane, and you can see it decreases, but it doesn't decrease anywhere near as fast as the hydrogen, which is burning away a lot faster. That's the kind of thing you see. So let's jump from there to something more biological. The point is, it's going to be much the same but not quite. So let's look at bacteriophages, which are viruses that infect bacteria. This is a T4 E. coli bacteriophage. That's the anatomy of a bacteriophage. The main thing is the head, because the head of a bacteriophage contains the DNA that codes up for the whole bacteriophage, including the head itself and its arms and legs and injection mechanism. So how does it work? Here's a little. Biology is much more fun than computer science. You can get any number of pictures off the web. So here's a viral infection happening. Bacteriophage lands there, injects its DNA. It's a DNA virus. The DNA goes into the nucleus of the poor bacterium. Once it's in there, the bacterium starts making all the components of the virus. It makes more copies of the DNA. It makes more things which will assemble together to make viruses which explode out of the cell, killing it. So that's the life cycle of a virus and the rather short life cycle of the infected bacterium. So here's the same thing in rules. Okay, what do I want? This is what's going on inside the cell. I just want to point out a couple of points in these rules here. So this is the genomic viral nucleic acid. That's the thing that was in the head. This is the template viral nucleic acid. That's this thing implanted in the DNA of the host organism. So it implants first at some rate. Once it's in, it can produce more STR, which is the viral structural protein. That's all these bits and pieces it needed to make the head and the legs and so forth. Here it's rather simple. And it gives more of what should be in the head, the gen. It keeps producing these things. Sometimes things can just vanish. So that's still chemistry, but this bit isn't chemistry. This is how viruses and cells infect cells. Suppose you've got a virus in a cell, then you come and infect a cell, and inside the cell, you have a copy of the viral genome and some other stuff. So you see what's happening. This is just like what we had before in our abstract syntax. We have expressions. We have function symbols. Previously, it was plus. But here it's, I'm an infected cell, or I'm a cell. And inside it was plus of 2 and 3. But here it's, I'm an infected cell, and inside myself, I have this piece of DNA floating around, and possibly other stuff. So there's, for example, a reaction. Suppose I'm an infected cell, and I've got enough stuff to make a virus. Then a virus can appear outside me, and I'll remain OK. Some viral infections don't kill the cell. This is an example of one that doesn't. And then you can simulate that. And I think I know what I need to say, so I'll just say we can go back to that if anyone wants to see afterwards. And I want to go on to something else. I want to give some feeling of the kinds of things that happen in bacteria, in biology. So what you have to do, I think, you have to be useful, you have to speak the language of the people you're trying to be useful to. Actually, people don't want you to be useful for them. They just tell you to go away. But that's the real truth for a lot of the time. Anyhow, you have to speak the natural language of biologists. And at the same time, we have to get something that works. So that was for location. That was for how things are related inside each other. That happens a lot in biology. The other thing that happens a lot in biology is that things connect up, that we have complexes. So here's your blood. This is a hemoglobin. It's a protein complex made out of 4 units, not 2 alpha ones and 2 beta ones. And of course, being computer scientists, we immediately reduce that to a much less interesting looking picture. And this is an example. Oh, sorry, of 2 proteins A and K, and these kind of somehow bind together. Well, we just say, okay, there's a binding sites A and B, and whoops, here A and B are unbound, and one move later they become bound. And this is to do with phosphorylating. I guess I won't bother telling you what phosphorylating is at this speed. It's just something that's going to happen. Once these have been connected, this can phosphorylate that. So this site here is not phosphorylated, but here it is. Phosphorylated, sorry, just means there's a phosphate group attached to the protein at that point. So that's pictures, but you can turn it into rules. You get more rules, glorious rules. So there's A, and this protein A at site A is open. This protein K at site B is open. And after they've gone together, there's a line which we're going to call X connecting them. They're no longer open. So what I'm trying to say is that there's things that happen in biology, the way biologists talk, and we can write them down in rules quite directly and quite naturally, and we can run these rules. We can run these rules. For example, you might be interested in signaling. If a cell receives a signaling via a signaling cascade, we can that signaling cascades are generally made up of groups of proteins bound together in complex forms, and these groups are then bound together in supergroups. It's very complex, but this kind of thing can perfectly well simulate it, and there's a bunch of rule-based systems of that kind. There they are. And I just want to say, just like structural operational semantics might not have seemed so useful, but perhaps surprisingly it has had uses. I just gave you one. There's actually quite a few. I mean, it's much less surprising that this thing has had uses, but the uses have mostly been modeling biological systems, perhaps finding out a little bit more, but we're beginning to see we might actually get some human benefit out of this. So, for example, if I take the biocam system, you looked at the G protein signaling. G protein signaling is the main mechanism that cells use for signaling. And it's like the most important thing, not the most important thing, it's extraordinarily important in medicine because the G protein receptors provide 40% of current drug targets. So that's a big deal. So the question is, do we actually know how these things work? And so recently they found out we didn't actually know how these things work. This guy, Lefkowitz, is the guy who got his Nobel Prize for working on G proteins. And what they did was they ran a simulation. Now, bacteriologists know everything about, molecular biologists know everything about these simulations in terms of the non-quantitative way that we're doing it earlier with chemistry, but less is known about the quantitative aspects. And so in this case, the model didn't fit the data. And so they had to change the parameters by using learning to get parameters that did fit the data. Once they found parameters that did fit the data, they found that a certain thing called a kinase was more important than previously realized, and it actually affected the balance between two different signaling pathways which can be used in different occasions. So to put it crudely, more is known now about how this pathway works than before. This is another example. This is an example in colon cancer, where in colon cancer, elevated beta-catenin levels are implicated in colon cancer, but people didn't understand or don't understand why your beta-catenin gets elevated. And so this particular paper proposes a mechanism why it gets elevated. And again, you need the quantitative information to know that. And it also identifies a possible drug target. So they're about to do some experiments to see if this drug target really is useful. So one should be modest, but one might feel quietly hopeful. Now, the question is, what's going on? Suppose we say, this is great, let's just, do science fiction, let's just simulate all of life. I'll just simulate your entire body, and I'll answer every question about your entire body. Well, of course, that's kind of a nonsense. In fact, what we were doing before, just single cells are unbelievably complicated. We're only scratching the surface. So all I'm actually pointing out in this slide is, no matter how complicated single cells are, the whole story is much more complicated. It's multi-scale. So the scale here is ranging. If you look at a whole man with a few arms and legs, that's about a meter, 3 meters, a meter to scale. If you look at say protein interactions, we're down, what's that? I can't read. Anyway, down here is 10 to the minus 10. So that's a tenth of a nanometer. So that's an enormous range of scale. And people do modeling at all these different ranges of scale. These are some of the techniques. These are experimental methods for finding something out. And it's kind of interesting to look. You see ordinary differential equations. You see spatial partial differential equations. You see cellular automata. You see so it's a kind of mixture of computer science and physics. That's kind of exciting. So what I want to say is, at the beginning of the lecture, it was a contrast between physics and computer science, or chemistry and computer science, or biology and computer science. But when you're doing simulation, things come together. So our final slide is the same as the first slide, but not quite. Because in fact, if you're simulating in physics, you don't actually run partial differential equations in your computer. You run discrete versions of them. So everything gets discretized when you're doing simulation. The states that we were simulating before are perfectly continuous. I didn't say why the state was continuous. That would take me slightly far apart. But certainly dynamics was continuous because it was continuous time that was being simulated. So in fact, through the simulation spectacles, there's not a big difference there, but there's still a big difference there. And in fact, you can see it. Here we're using a cellular automaton. Here we're using an ordinary differential equation. So, and you can actually look. If you take particular examples like the the chemical reaction rule, that corresponds to a differential equation. And you can give a semantics, actually a denotational, not an operational semantics, in which the semantics of a rule is a different set of differential equations. So some rules do correspond to equations, but other rules don't. And not all equations correspond to rules. So the question is, how can we work together? Maybe rules will still be there, differential equations will be there. We need to understand how it all works together. So having started maybe in 1900, it's a bit later now, I think there's still a huge amount to do. This is just one simulation subject, and I hope you've enjoyed this lecture. It's been my pleasure to give it, and I hope it gives you some feeling for the importance of language and the non-isolation of language from other parts of science. Thank you. Okay.
Wow. I've been asked if anyone would like to ask a question, they're very welcome to, but could you identify yourself and wait for the microphone to appear because of the recording? Any questions?
I rarely.
There,
great.
back there.
I'm afraid it's just the second or third slide. You had an expansion. I think it was just x plus y, or x plus 1 in a bracket multiplied by y, something like that. And I didn't think the expansion was correct. You had put plus 1 instead of plus x at the end.
Oh, yeah.
That's the only error I spotted.
And you worked carefully through all of them, did you? Thank you very much. I'll correct that straight away.
Another question? Phil.
So the stuff about Emil Post was very interesting and not something that I knew well. But it was a very interesting story. It wasn't clear. So because of these gaps where he did the work but it didn't get published, was there a direct line from his work and your work, or did you only discover later, oh, he beat me to it?
I don't believe he beat me to it. I don't think we did quite the same thing. No, I didn't find out about Emil Post properly until I was preparing this lecture. What I was directly influenced by was Raymond Smullyan's work. Raymond Smulyan is directly influenced by Emil Post. Yeah, so it's the intellectual roots, not the personal roots are another matter.
But there is a direct line.
There's a direct line. Yeah, the other guy who was there was Andrei Markov Jr. There's a similar kind of systems that he had, but I think I was less influenced by them. Trouble is, I can't quite remember. It's a while ago. But anyway, in either case, both of them went to Emil Post. He was the primogenitor of this kind of thing.
Anyone else got a question? So I have a question. I have a microphone, so it's okay. So is the same theorems applicable across this incredibly diverse range of things? Biology?
No, I mean the first theorems. You mean the theorems at the very beginning theorems?
I mean the general properties of operational semantics rules.
No, I don't think so. Because, for example, the operational in these rules, there are commonalities. For example, so there's a matching problem with these rules. So with the biological thing, you have to here's a rule. You have to say, okay, yeah, it says that these two complexes they do something, and it's expressed by a rule. And you have to find where there are such complexes in your state. The state is the kind of the assemblage of all proteins, and that turns out to be a matching problem, but it turns out to be a matching modulo certain axioms, associativity axioms. But then the point is in biology, you want to do quantitative things, so you have to not only do matching, but count the number of matches. So this is stochastic rewriting, and that is a subject that doesn't exist in rewriting, and it ought to. And so I think that's kind of a lesson for computer science. So commonalities and differences.
Question over there.
If we could, Jeffrey Bolton from Edinburgh University, if we could clone Gordon Plotkin and send all these clones out as missionaries into the scientific universe, then would they find lots of problems to which they could contribute?
Well, that'd be great. Yeah, I'd love that.
Or are you simply describing a niche that you've discovered, or is there a broad applicability to the sort of approaches you've been describing?
Well, I don't know how you define the word broad. That was moderately broad. But
it was only a bit of biology, after all.
If we take climate science, for example, no, I think there's lots of areas that, well, I think simulation in general is really interesting. And it's done throughout science, and the general feeling I have, and the thing is, I'm really ignorant here, maybe in fact you're much less ignorant than I, is that computer science could do a lot more to help people who are simulating things. I mean, for example, an example problem I happen to have heard about in climate science is that climate scientists build their models using GPUs. Well and good, but GPUs keep changing. Every Thursday there's a new kind, and they have to keep rewriting their models, the poor things. That shouldn't be their problem. There should be a kind of proper solution. I've also heard that physicists don't know how to write code. They don't know, but they don't know how to do structured. I don't know if this can be true. Actually, I should be very positive when I'm speaking here. We should see if we can help them, and we shouldn't be surprised when they don't want any help, and maybe they don't need any help, but we have responsibilities to go out and have a look.
The speaker over there. Question.
When you're using, Sean Jones, when you're using mathematics to model a biological function, how do you go about validating that model to make sure that it is something worthwhile and it might not? Do you have a validation process to make sure the model is satisfactory before you start using it?
Well, you have all the data in the biological literature, and you try to reproduce it.
So what you're trying to do, you're seeing whether it matches up.
Yeah. And in fact, in that first one, it didn't, you see. And that was kind of interesting. And then one had to do parameter estimation to find ways in which it did match up. Yeah. Actually,
do you think it's enough? Do you think it is enough just for it to match up, or do you need to do anything?
No. Once it matches up, then you've got a model. Then it makes predictions. Then you have to do experiments to see if it's really right. But one of the really great things about these models is they're cheap to run. I saw this amazing statement that every paper in Nature costs £1 million. $1 million, sorry, it's cheaper. It's just really expensive to do experiments in biology. So if you can do moderately reliable experiments in software, it's a breakthrough. Or it would be. So there's one point I should make, which is the idea of using mathematics in biology is really old. I mean, Julian Huxley, it's all kinds of mathematics we've been using in biology for many years. This is just a little bit of language added in, a little bit of computer science. Mathematics has always been there, in general.
There's a question.
Krzysztof Abt from University of Amsterdam. I wanted to ask you about the role of the rules in education of mathematics in secondary school. Because if you look at the textbooks, then essentially what those kids have to learn is to operate rules. How do you write sinus of 2x? How do you compute the quadratic equations? How do you compute derivatives? These are all rules. How do you compute integrals? So essentially, mastering mathematics in secondary school, excluding geometry, seems to be a proficiency in using rules. And most of the problems are essentially a combination of finding right, let's say, usage of these rules, which will bring you to the solution. So like in primary school, you learn things by adding and operating on numbers. And in secondary school, you learn to operate on expressions, which you mentioned. So is there some niche there to use this approach to mathematics?
Well, I can tell you I'm completely uninformed about proper ways of education. but my reaction is one of horror. I mean, what I said about these rules, the point is this is the formalist approach. There's no meaning whatever. Rules are things one can apply mechanically. So you're not going to learn anything by applying rules except how to apply the rules. So you shouldn't, but maybe you're not suggesting one should only apply rules.
70% say of mathematics in secondary school is mastering those rules.
And therefore what?
And then you are supposed to understand mathematics by mastering those rules.
But that's false. One doesn't.
Yeah, but that's how you get good grades.
Well, there's lots of programs that can apply rules automatically, so you can just give every child a program. I mean,
So I have a script I have to follow, and we're running out of time. Is there one more quick question? Over there. Quick question and quick answer, please.
This is Manfred Breuer from Munich. I have a question. You didn't talk much about abstraction. I think there's an interesting relationship between operational semantics and denotational semantics. Could you say a few words about that too?
oh, I'm trying to think. Yeah, well, this won't be a widely comprehensible response. But operational semantics has been wildly successful. One reason why is maybe Shistof's point. It's dead easy to do. You can write rules. You can write rules to do anything, however barbaric, however you misunderstand it, you can write your rules. Whereas I like to think that denotational semantics is a little bit more confined and disciplined. And I think it gives the underlying structure. And I've got a general interest, sorry, Mike, in marrying the two. But I'm constrained to reply briefly.
Yes, Professor Plotkin is, of course, a world expert on that subject. So now comes the time where I look for his award. There is no order specified. I scroll. This is your scroll.
Thank you.
For the first winner of the Royal Society Milner Award. I suspect this is your enormous check. And this would be your medal.
Thank you very much.
So congratulations.
Thank you.